I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just pray you bless this time today, Lord. In your name I pray. Amen. All right. So I have a few things to tell you today. So I'll try to hit the high points in the numbers section. That I projected some of this stuff last time, but it should be written on the board. Number one, the definition of a left multiplication map. All right, so L sub alpha from A to A given by L sub alpha of x is equal to alpha times x. And here, of course, I'm assuming that A has multiplication. All right, so I'm again talking about an algebra, and this is the left multiplication map. We say that R sub A is equal to the set of all such L alpha. This is called the regular representation of A. All right. As I discussed in the notes, if the mapping is in the regular representation, it follows that it's right linear. So observe, you go through that calculation right quick. If we have L alpha of x times y, all right, that means alpha times x times y, but then by associativity of the algebra, we can rewrite that as alpha times x times y, right? And what that is that's L sub alpha of x times y. So this property, going from here to here, this is what I call right A linearity. All right. In other words, that you can pull a multiplication in the algebra out to the right of the argument of such a function. So every left multiplication has right A linearity. Now, next, I introduced a different kind of representation, which is what we mostly use in here, which is the matrix representation of A. All right, so the matrix representation of an algebra. So here, we're taking our algebra to be Rn as a point set. And so the matrix representation, M sub A, is equal to the standard matrix of L alpha, such that L alpha is in the regular representation of A. In other words, to put it into words, the matrix representation of the algebra is simply the set of all standard matrices for left multiplication maps. All right. And I also define a map. I say M is a mapping from A to Rn by n given by M of alpha equal to, here's how it goes, L alpha of, well, to get straight to the point, it's alpha times E1, alpha times E2, alpha times En. So that's how you figure out the matrix which represents a given number. Now here, E1 through En are just the standard basis elements, like 1, 0, 0, 0, or 0, 1, 0, 0, and so forth. If E1 is just the identity in the algebra, all right, so if E1 serves as the multiplicative identity of the algebra, then this formula for the matrix representation is even nicer. And that's almost all of our examples. M of alpha is just going to be alpha, and then alpha times E2, and so forth and so on, alpha times En. And so often that's how we can calculate the matrix which represents a given algebra. So in the notes, I derive the representation for the complex numbers from that, right? Let me just do one example here. Let's look at the algebra equal to the hyperbolic numbers, all right? So that's x plus jy, such that x and y are real numbers, and j squared is equal to 1. So basically the notation here, very simple. It's E1, which is of course 1, 0, that's equal to 1. And E2, which by the way is 0, 1, is equal to j. That's our standard notation for the hyperbolic numbers. Just like for complex numbers, our standard notation is 1, 0 is 1, and 0, 1 is I. Right? So the matrix representation of, let's say, A plus Bj is going to be A plus Bj, and then A plus Bj times j. And we have to multiply that out. The reason it's just the number again in the first column is because the E1 is the identity here. All right, so we just put the number in the first column. And then we put the number times E2 in the second column. But here E2 is j, and that simplifies to what? Right? Because j squared is 1, so j times j is 1, and we have b plus aj. And then rewriting it in our usual matrix notation, this is ab, ba, which is that matrix representation for the hyperbolic numbers that we saw last class too, right? Let's do another one to make sure you guys understand this. This one's kind of a fun example. Quaternions are, well, here's a way I could write it. I could say it's R, direct sum IR, direct sum JR, direct sum KR. And all this notation means, guys, is it's something of the form T plus XI plus YJ plus ZK, such that T, X, Y, Z are real numbers. And here we have I squared equals to j squared equals to k squared equals to minus 1. And ij is equal to k, jk is equal to I, ki is equal to j, etc. And also ji is equal to minus k, kj is equal to minus I, ik is equal to minus j. Now, you can get away with writing a lot less than that, like a minimal set of generators for the quaternions. I think if you just say, oh, I forget the minimal set, but these things are all true. So you could define it this way. It's just a very heavy-handed and unnecessarily redundant definition, all right? But these are quaternions. So these are the things that Hamilton searched for about more than a decade, right? Trying to extend complex numbers. He was trying to find a three-dimensional number system that behaved like complex numbers. And he finally gave up on it and realized, oh, but there's a four-dimensional system which behaves like complex numbers, and these are called the Quaternions, right? Now, I've written down three-dimensional algebras which allow multiplications last class, like the three hyperbolic numbers, things like x plus yj plus zj squared. We looked at that one. So that's a three-dimensional number system, but it was not the kind Hamilton was looking for, all right? And I'll talk more about why that is today. But it has to do with the way the norm works, where norm is the idea of the length of a number, all right? So here, what's the matrix? So what we're going to do is we're going to say E1 is 1, 0, 0, 0. E2 is what? I. E3, J. E4 is K. So the matrix representation, and I'm tired of, let me call this thing, for lack of imagination, I will call it Pac-Man. All right, so let's call the number T plus Xi plus Yj plus Zk Pac-Man. So the matrix representation, so here's just an overarching guide for we're going to calculate the matrix representation of this quaternion, Pac-Man. And by my usual rule, since the identity is the first element in the standard basis, we put the number in the first column, then we put Pac-Man times what? Nom, 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 I. Pac-Man, nom, 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 J. Pac-Man, k. It matters. It actually matters that we put the I, the j, and the k on the right and not the left in this case, because quaternions are not commutative. They're just barely not commutative, though. They're kind of almost commutative, in a sense. That's kind of a lie, but all right. So the first column is just t, x, y, z, right? And I'm gonna work them off over to the side here, and then just write down the corresponding, vector like I just did. Pac-Man times I, what's that going to be? It's going to be ti. What's I squared? Minus x. What's ji? Ji is minus k, right? What's ki? Ki is j. So I believe in the next column we have a minus x, a t, a z, and a minus y, if I did it right. I got two minuses over there, right? What's Pac-Man times j? I'll do these. Tj, right? What's I times j? That's k. What's j times j? Minus 1, right? So minus y. What's k times j? K times j minus I, so minus iz. So let's see here. That puts a minus y up here. And then my I component is minus z. My j component is t. And my k component is x. So if I understand the pattern here, we should find two minuses in the next column, right? Do you care to tell me what the 4, 4 component is going to be without even doing any calculation? Can you see the pattern here? It's got to be t, right? So let's work it out. So Pac-Man times, what was it, k? So I get tk. What's ik? Ik minus j, so minus xj. Jk is, what is jk is I plus yi. And then what's kk? Minus c, yeah. All right, so what we got is we got ourselves a minus z. We got ourselves a y here. And we got ourselves a minus x here. So there you go. That 4 by 4 matrix represents a quaternion. If you study the matrix multiplication of such sets of 4 by 4 matrices, they will be isomorphic to the quaternions as an abstract number system. And we can decide whether or not the quaternion is invertible by checking if the determinant of this matrix is non-zero. So what condition what condition does it take for the quaternion t plus xi plus yj plus zk to be invertible? We just got to calculate the determinant of this here 4 by 4 matrix, right? What's the determinant of M of Pac-Man as above? Yes. It is perhaps some number times the sum of squares. Now, I have not worked that out, but I'm telling you, that's what it works out to. And that is why we say that quaternions form what's called a skew field, in the sense that every non-zero element has a multiplicative inverse. It would be a field, except that it's not commutative. So quaternions are really a weird thing. And you can define Pac-Man bar to be, like t minus xi minus yj minus zk, like that. You can define a quaternionic conjugate which flips the signs of everything. And I think like Pac-Man times Pac-Man bar is something something nice. I forget exactly what it is, but it's something nice. May actually be the sum of squares. Yeah.
Is it useful in general to, like, define in the notes you have the real and unreal parts to say define the conjugate to be the real part minus the unreal part?
That is not actually how we'll define conjugate. You might think the conjugate would be defined as the real part minus the unreal part. But actually, our notion of conjugation, as we'll discover maybe, I don't know if it's going to be this week, maybe next week, is something much weirder.
Is it similar to the notion of conjugation for fields like constants?
No. The conjugation for fields that Samuel's talking about, so for fields, the notion of conjugation is something more like complex numbers. Complex numbers, complex conjugation gives you a one-to-one mapping from the complex numbers to itself, and it's also an isomorphism in the sense that the complex conjugate of the product is the product of complex conjugates. Complex conjugate of a sum is the sum of the complex conjugates. It's actually a ring isomorphism in the sense of abstract algebra. And so those Galois conjugates that Samuel's talking about are more like that. The conjugation that we'll talk about in here is not algebraically nice, but it serves the purpose of calculus. I'm getting way ahead of the story, so, but good question. Anyway, I thought I should do this calculation because you should see a couple of them at least. Like this one is definitely harder than the one I asked you. And the calculation of this determinant is a pain, right? That would eat 10 minutes of class for me to do it. But I know that's what it works out to. I don't know what number goes there. It might be 4, right? It may just be 1, I'm not sure. Okay, so notation, I should share with you guys. Definition. We say U of A is equal to Z in A such that Z inverse exists. Meaning what? Z times Z inverse is equal to 1, right? So in other words, the set of invertible numbers we call the units of A, right? And we also define, and this is notation. I don't know if this is I couldn't find a standard. U of A is a fairly standard notation that exists outside this discussion. You'll find lots of like abstract algebra books which use U for units like that. I'm using this notation right now in abstract algebra if you're in there with the same meaning. But what I'm about to write, zero divisors, is a notation I made up. I can't find a standard notation. But it's a standard idea. So zero divisors of A is Z in A such that there exists W not equal to 0 such that Z times W is equal to 0. Or W times Z is equal to 0. I really am only interested in the commutative case for zero divisors, so don't sweat it. Admittedly, theory for non-commutative case is only partly fleshed out in my thinking. Anyway, so we have zeros, we have units, we have zero divisors. Fun theorem about zero divisors is the set of zero divisors is fixed under negation. Think about this. If x is an element of the zero divisors of A, then minus x is an element of the zero divisors of A, right? How would you prove that? It's very silly, so look at it. It's if there exists, W in A such that what? W not equal to 0. X times W equal to 0, then what's that say? We can multiply by minus x, right? Times W is also equal to 0 by the properties of the algebra. I say that not so much because it's a hard thing to prove, but because it's very useful as you're trying to understand what the set of zero divisors looks like in a given algebra. All right, so if you discover there's like a ray of zero divisors going off one way, you can rest assured that the other half of that ray that points the opposite way is also zero divisors. In other words, zero divisors are things like lines, or planes, right? But in the sense that they're fixed under negation, but they don't have to be, they're actually end up, what I've seen in examples, that the set of zero divisors tends to be like a collection of lines or planes, not necessarily of the same type. Like you could have a plane and also a line. I think geometrically that's what you'll find for that, the three hyperbolics is a plane and a line put together if you look at it right. Yeah.
So they're also closed under multiplication by a scalar.
Right. Yes. You can rescale a zero divisor. It still have a zero divisor. That is also true. Now, theorem 3.1.10 says the following things. It says that map M I was talking about a second ago, right? The mapping from A to the n by n matrices. I call this the representation map sometimes, all right? The representation map is in fact an isomorphism in the following sense. And I know you guys don't know, maybe you don't know what an isomorphism is, and that's okay. For you, this is just a useful theorem. So this matrix, I mean, the word isomorphism is less important than the formulas I'm writing down right now, okay? The matrix, the representation map, it maps the number 1 to the identity matrix. This identity matrix is this thing. And 0 is off the diagonal, all right? It's linear in the sense that the matrix map of Cx plus y is equal to C times the matrix of x plus the matrix of y. And 3, and this is the one I've asked you to prove in problem 10, is that the matrix of x times y is equal to the matrix multiplication of mx times my. Let me prove 2, so that you have some sense of how you'd prove 3. It's not that bad, really. So here it is. So first of all, definition. The matrix of x is what? It's the standard matrix of Lx. And I better not use x here because I used x in a different sense there. So let's say alpha like I was before, right? Left multiplication by alpha. So let's see here. Oh, actually, I'm an idiot. So the matrix of Cx plus y is what? That's the standard matrix of left multiplication by what? Cx plus y. However, notice that L of Cx plus y acting on z is what? So by properties of the algebra, that's c times x times z, by the bilinearity as I called it, right? Which is c times Lx of z plus L sub y of z, which we can rewrite as CLx plus Ly, all acting on z. So what I've just shown is that for any input, left multiplication by Cx plus y is the same, the output from that is the same as if I take the mapping C times Lx plus Ly and let that act on z. Right? In other words, this equation is true for all z. So therefore what? Therefore L times Cx plus y is actually equal to CLx plus Ly. So not only is L sub alpha a linear transformation with respect to its input, it's also a linear transformation with respect to the number which it labels. But long story short, that means that this is equal to CLX plus LY, right? And then I just use a little fun fact from linear algebra, which is that the standard matrix of a sum of two transformations is the sum of the standard matrices of those transformations. So at this point, I rely on linear algebra. This is C times the standard matrix of LX plus the standard matrix of LY, which is C times MX plus MY. So that's why I gave you guys that hint in problem 10 about the standard matrix of a composite being the product of the standard matrices, because that's the step that you need to prove part 3, very much like what I just wrote in red. Analogous to. But, all right. In any event, whether or not we understand all the nuts and bolts of the representation map, we have it to work with, and one of its critical uses is the following theorem, which is that U of A is the inverse image under the representation map of the set. I'm going to regret starting to write here. I need to give myself more room. Theorem. If I want to calculate the units in the algebra, one way I can do that is to find the set of all matrices, which maps under the representation map. Well, this is actually the inverse of the representation map. Let me stop talking and keep writing. So can you guys tell me how to, the proof of the theorem is in the notes, but I thought I should tell you this much. What's the inverse of a matrix A under this map? Let's suppose M is, the usual representation map from the algebra to n by n matrices. And let's suppose that E1 is the identity. What's the inverse map in this case? How do you find the number which maps to that matrix, which is represented by that matrix? What have we learned? If E1 is the identity, the number is where? It's in the first column, right? So if you want to undo the representation map in this context, you just select column 1 of the matrix. That's it. That's the inverse map. So not only is there an inverse map, it's actually fairly concrete and reasonable to write down once you know the identity. If the identity is like the jth basis element, the inverse is just the jth column. That's what the number is that's represented by the matrix. Okay, fine. If the identity is not the standard matrix, it's not one of the standard basis. If it's like a linear combination of them, then it's messier. All right, but now what I'm saying here in the blue is simply this: to find the units, all we have to do is find the set of matrices in the representation whose determinant's non-zero. Such matrices represent numbers which are units. So we put the M inverse to get back to the numbers which are represented by such invertible matrices, and vice versa for the zero divisors. Right, same story. So like, what's the zero divisors for the quaternions? Well, I said everything's a unit, right? Except for what? So one thing that's not a unit in the quaternions. Whoa, it's got an HDMI thing now. Cool. I was expecting to have to get out my adapter. I always have to get out my adapter in this room. But they've got some kind of new, oh man, it won't. This thing is very difficult to like twist to the orientation. There we go. Come on. and make sure I don't have student IDs on my desktop. I hate editing. So for the zero divisors for the Quaternions, it's just the 0. 0 is the only zero divisor. Okay, so you might say, well, a zero divisor has to be non-zero. Well, this is, we can, yeah, sure enough, it was an email we shouldn't look at. Let's see here. I'd like to say I'm getting smarter, but let's not get carried away. Let's see here. Come on. There we go. So I wanted to write these things out on the board because it's important for you to understand what the notation means, because we're going to refer to it here and there in the next, couple lectures. So try to wrap it up here. I will not cover all of the examples, but this idea right here is pretty important. So you're fine. I just always forget to. All right, so if we have an algebra A with multiplication star and B is another algebra with multiplication diamond, then A is isomorphic to B if there is a linear bijection psi going from A to B, which changes stars to diamonds in that sense. All right, so it preserves the algebra structure. It changes that multiplication to that multiplication. So an interesting algebra which I have not introduced yet is this R cross R. This is the direct product algebra. And sometimes when you feed stuff to Wolfram Alpha, it tries to use this thing. Sometimes when if you put this into Wolfram Alpha, there's a chance it's going to multiply that like the following, right? 1 times 3, 2 times 4, right? That's actually, this is the multiplication in R cross. So the direct product of R and R, this is the so-called direct product algebra. Direct product of R and R. Generically speaking, you could take two algebras and take pairs of numbers from each, and if you want to multiply component-wise, you can form this product algebra to make a bigger algebra, which is based on these two algebras you're forming the product of. So it turns out that R cross R, with this really easy multiplication, just multiply x components, multiply y components, that is isomorphic to the hyperbolic numbers as it happens. And the isomorphism actually is given by the following formula. Psi of AB is equal to A times 1 plus J, B times 1 minus J over 2, and here's the inverse map. All right. So, for example, we learned that a zero divisor of the hyperbolic numbers was like 1 plus J, right? So what is 1 plus J here? What happens if I put 1 plus J into this inverse map? 1 plus J gives me what? X equals to 1, Y equals to 1. What's my output? 2, 0. So isomorphisms preserve zero divisors, like the isomorphism is going to take a zero divisor to a zero divisor. So one of the things I'm telling you, among other things that you can glean from this isomorphism, is that there's a zero divisor in R cross R, which is 2, 0. In fact, both E1 and E2 are zero divisors in R cross R. Why? In R cross R, check this out. So if I have like 1, 0, times 0, 1, what do I get? I get 0, 0, right? So E1 and E2 are themselves zero divisors in the direct product algebra. All right. So they're the zero divisors, and they're not weird things in the direct product algebra. They're just kind of sitting there looking at you, right? They're hard to miss. What's the identity in the direct product algebra? It's actually E1 plus E2. And you can see that also from here. If you look at plugging in x equal to 1, y equal to 0, what comes out? You get 1, 1. Right? Anyway, So the identity in the direct product algebra is 1, 1. I think this example is interesting, though, because it shows you a little bit why isomorphism is something you might want to think about for certain problems. If you were going to solve the quadratic equation in the hyperbolic numbers, it's kind of a pain, right? In other words, I want to solve z squared plus bz plus c equal to 0. Well, I could instead trade that for the isomorphic equation in the direct product algebra using this isomorphism. And because the isomorphism breaks up across addition and multiplication, it changes into this corresponding quadratic equation for the direct product algebra. If I introduce notation, like that's v1, v2, that's c1, c2, then this equation 3.5 is just xy squared is b1, b2, xy, c1, c2, right? And if I simplify that further, that's actually x squared plus b1x c1, comma y squared plus b2y plus c2 equal to 0, comma 0. And I think all of you can solve this one component at a time, right? That's just a real quadratic equation, comma, a real quadratic equation. The solutions are given either to be none, just 1 because it's a repeated root, or 2, right? So if you do the counting, that means that a hyperbolic, the quadratic equation in the hyperbolic numbers either has no solutions or what, 0, 2, or 4 solutions to a quadratic hyperbolic equation. Now, this method of argument is not possible for problem 8. When I worked out problem 8, I either found 2 solutions, no solutions, or infinitely many solutions. And the infinite many solutions was contingent on a rather peculiar relation between the components of the coefficients defining the dual quadratic equation. My solution's about 2 pages long for that one. That one's not, it's not hard, but it requires persistence. So what I'm trying to say is the quadratic equation in the dual numbers is kind of a drag, right? On the other hand, here's the reciprocal of the dual numbers. Not too bad. 1 over a plus b epsilon is a minus b epsilon over a squared, provided a is non-zero. So all the units in the dual numbers are of this form. Now, I'm not proposing that you know the inverse for every single example that I'm giving you. I'm just trying to illustrate to you enough that you have a sense of how you'd figure it out, and also have a sense of the fact that we know so much about complex numbers, right? But if you start trying to ask those same questions about other number systems, it could be like a whole semester's work for you to figure it out. I mean, to really figure it out. There's a lot that's not known. Or if it's known, it's not known to me. All right. So anyway, the rest of the examples here are great. I should mention that these guys are kind of funny. This C3, which is defined by a unit which cubes to -1, these are the so-called complicated numbers. Yes, I know. In the case that k squared is -1, the complicated numbers are just complex numbers at their lowest order. But you can prove that complicated numbers of odd order are isomorphic to hyperbolic numbers of odd order. Here's the complicated numbers of order 4, and that's the matrix which represents them. These kind of matrices are called skew circulants. There is some connection between these matrices and studies of primes of the form 8n plus 1 or something like that. There's papers by a mathematician by the name of Good, who has a lot to say about these things. Anyway, so there's a bunch of examples. We don't have to look at them all. The last example is kind of cute if you know group theory. If you have a finite group, right? For those of you who know group theory a little bit. Some of you are just starting to learn a little group theory. If you took a group with finite many things, you could just basically assume that the group elements were linearly independent, and this would define an algebra of dimension of the group, where you just multiply things according to the group rule, and that's it. This is called a group algebra. Not every algebra is a group algebra, but those that are pretty cool. The hyperbolic numbers, for example, are the group algebra of the cyclic group of order 2. The n-hyperbolic numbers are the group algebra of the cyclic group of order n. Now, if you don't know what cyclic group of order n is, that's fine. I don't know if this even matters. It's just something I was messing around with, okay? But I've defined an unreal part. So you can look at that. I'm not sure what to do with this at the moment. It's a curiosity for me. So that brings us to chapter 4, which is on topology and analysis. So we need to talk about topology. And so what I'm after in this chapter is simply this, is to define for you what is a limit for a function over the algebra, what are the limit laws, and to try to prove some subset of those things, all right? So I'm not going to be able to prove much today, but I think I can introduce the terms at least, all right? So the main thing is we're going to say that A, which is of course Rn, has the norm of, let's say, x1, x2, xn. What's the norm going to be? It's going to be the square root of x1 squared plus x2 squared plus plus xn squared. This is, of course, the beloved Euclidean norm. Now that's our choice, and that's the one I stick with. So with respect to this Euclidean norm, we can do things like define limit and open ball. So what's an open ball? B sub epsilon of x naught, what's that going to be? It's going to be the set z, well, let's say x. I guess I should use a z. Sorry, I'll get with it eventually. Whatever, it doesn't matter. The letters. So z and a, such that what? Such that the length, the norm of z minus z naught is less than epsilon. So this is called a ball of radius epsilon centered at z naught. Here's a picture. Typical point in there. I mean, I can draw this picture. Does it really help you with anything? I don't know. Maybe it does. Maybe it doesn't. I'm not sure. I'm not sure that picture is really any better than this one, because this is what the ball looks like in radius in dimension 2. Right? In dimension 2, the ball is what? The ball is a disk. Now, I have taken these notes, and I have, so this displacement vector right here, right? This one going from here to here is what? This is z minus z naught, right? So what we're saying is that the distance to points in the open ball of radius epsilon are less than epsilon from the center. And in 2 dimensions, we tend to call the open ball an open disk. Now I've taken, what I did here of this sections, I took my complex notes from before, and I've changed every time I said disk, I changed it to ball, because we're working with possibly 2 or 3 or 4 dimensions, whatever. But the definitions are all the same, right? Right. So here's the definitions right here. If I can find my where'd I put my laser? Oh, there it is. So there's an open ball, which is just what it sounds like, a fuzzy ball. You can delete the center by putting this less than 0 here. That's a deleted open ball. You can talk about a closed ball that includes the edge, right? These are all things we can talk about. We have a set, which is a subset of A. We say that that point y is an interior point if you can find some open ball centered around y, which is completely in S. So a picture of that is like this point would be an interior point. Let me call that y, because I can find this open ball like that, right? And the open ball that I just drew around y is completely inside, if I'm calling S the bigger open ball. But S could be something weirder, right? S could look, I don't know, could look like this. It could have like half open, half not dotted, half included, half not included edges. And if you take a point like here, well, that's an interior point because I can find an open ball around it. All right? Interior points we can find open balls around. What's a boundary point going to be? Oh, first, what's an open set? An open set is a set in which every point is interior. A limit point of a set it's a limit point if every open ball centered at y contains points in y with S and y removed. And What's a boundary point? A boundary point is if every open ball centered at y contains points not in S and other points contained in S, right? So you can see why that would be, right? If this is a boundary point, right, and you take an open ball around it, you got the points inside and you got the points outside, right? So it's a good definition. So these definitions are all, for the most part, entirely geometric, all right? We also like to talk about domains and regions in this course. By the way, the boundary, the set of all boundary points is denoted in partial S. The closure of S is defined to be S union its boundary points, which I've said a little bit differently. Let's see here. A domain or a region. A domain is an open connected set. A region is a set whose, how does it go? A region has an interior, which is a domain, I think, if I remember right. Anyway, we'll get back to that in a second. To understand that word I just used, connected, we have to define that, right? So we talk about directed line segments. So this notation is a little bit funny, right? This is no longer for us, this is not the closed interval from A to B. In this context, this is the line segment from A to B. All right, this is a very useful notation because it allows us to do things like, say, the closed interval from 10 to 9. That makes sense. That's just the line segment that goes from the number 10 to the number 9 in the algebra. And we can talk about a set being star-shaped. It's star-shaped with star center Z0 if every point in the set can be reached by a line segment from the star center. So if this is my, I guess this is probably not, can you find a star center? I mean, I want to make that the star center, right? So like I can get here, 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 I can get here. But it looks like I'm out of luck, right? Because I'm never going to get, I'm never going to be able to hit these points down here, right? They'll never see the brilliance of my star center. So, but anyway, there are shapes which are star-centered, for example, disks, right? But an annulus wouldn't be star-centered. But you could divide an annulus up into pieces which were star-shaped. We can talk about a polygonal path. A polygonal path is a union of finitely many line segments, or you could call this a broken line segment. So a set is said to be connected if any 2 points in the set can be connected by a polygonal line, polygonal path rather. So technically speaking, that's the definition of path connected. So an open connected set is called a domain. All right. What's a region? A region, if we take the domain union with S, what's S? Surface? No. It's a subset of the boundary of D. So, okay, so a region is something like, it's a domain plus at least, it doesn't have to be the whole boundary of the domain, but at least some part of the boundary. So a region it's almost a domain. It's just got some funny stuff going on the edges. All right, like if you could imagine something like this would be a region. Like it's got half of its boundary, not the whole thing, you know. But if you look at the interior of that, that's an open connected set, which is a domain. All right, so these are some important topological terms. There's a theorem we can prove. If we have a continuously differentiable function on a domain, which is an open connected set, and we have that the gradient of that function is identically 0 at each point on D, then h is constant. And the proof of that is just the chain rule and the fact that when you look at the polygonal path, which we get because the set's connected, we can prove that the function h is constant on each segment, as is shown here, which then means that the function has to be the same along each segment. So connect the dots, connect the constant dots. So h is constant on such a domain. So that's just a very, very, very quick overview of topology in Rn, which is the same as topology in R2. It's just what's called metric topology, where the idea of open and close is judged by little open balls. All right. If you have more questions about that next time, I can draw more pictures. One other thing, the reason that what we're about to do is really, really different than just complex analysis has to do with the following unfortunate fact. For an algebra with multiplication, we don't have that the norm of the product is the product of the norms. It's just not the case. What ends up happening is that there's a submultiplicative constant. For the hyperbolic numbers, this submultiplicative constant is square root of 2. For other number systems, I don't know, although I do know some, thanks to Kang Nguyen, who has calculated them. Let me show you what he has found. So this is from last semester's 495. Kang figured out that the multiplicative constant for the n hyperbolic numbers is the square root of n. The argument that he used to prove that, it's quite beautiful. I'll show you if you want. So we have this inequality for the n hyperbolic numbers. For the complicated numbers, it's the same for odd n, but for even n, it's the square root of n over 2. For the dual numbers, he's calculated them for n equals to 2, 3, and 4, and 5. They are as follows. The submultiplicative constant for the dual numbers, 2 over root 3. For the 3 dual numbers, 4/3. For the 4 dual numbers, that. For the 5 dual numbers, that. For the 6 dual numbers, that. And here is the so-called sharpening elements, the place where equality is attained in these things. Now, do you need to know all this? No, of course not. But I want to draw your attention to the fact that we unfortunately do not get that the norm of a product is the product of the norms. We are stuck with this less glorious statement that the norm of a product is less than or equal to some constant times the product of the norms. For complex numbers, we get equality here, and the number's 1. So complex numbers are really, really nice. Same for Quaternions, and that's special. There's a theorem which says basically only the complex numbers and the Quaternions and the real numbers are normed division algebras, normed in the sense that the norm is multiplicative. All right, I've said enough for today. We will start next time with limits. All right?